My name is Avni Shah. I'm an associate professor of marketing here at the University of Toronto. I'm also the academic director and the site lead of CDL-Toronto, which is anchored here at University of Toronto's Rotman School of Management. I have the pleasure of having the conversation with these three amazing folks. I'm going to let them introduce themselves and talk about, just give a brief 60 seconds or less about who they are and their role that they played in the CDL community, because it's each of you have had quite a big role, and I think it's pretty cool. So, Michael, I'll start with you.
So hello, I'm Michael Helander, co-founder and CEO at OTI. We develop specialty chemicals for the consumer electronics industry. And we were actually an alumni of the CDL way back in the day, second year when it started back in 2013. We work on chemicals, materials, and so we heard from Ajay today about how AI for science is the golden goose that could lay the golden egg. My view is that the golden wheat that golden goose eats is new materials. And the reason why is that every scientific discovery, every engineering advancement, even software, depends on new materials with new properties and capabilities. So, you want to build a better bridge, you make it out of steel and concrete rather than wood and bricks. But the fundamental issue is that if you want to then say, okay, where do we get the wheat from? That has to come from a golden, wheat stalk. That is then, how do you simulate materials at a really high accuracy that matches the quantum world? Because all materials, almost all their properties, depend on quantum mechanics. This flower is pink because of quantum mechanics. And if you want to use AI, then you need good data. And so we came back to CDL, begged the team to let us send people back to start playing around with quantum computing with the hope that could let us do more accurate simulations to develop better materials and have that golden wheat we can feed to the golden goose.
Also a CDL mentor.
Yes.
Right?
Yeah,
Very
so
good.
I've been an alumni mentor for a number of years and went through the quantum stream again and then been a mentor since then. So it's been fantastic and great to see how many people flew in for CDL. Back when we went through it, there was a bunch of 30 people in a room and nobody flew in. And it's fantastic to see how the network has grown.
Amazing. Mark.
Hey everyone, I'm Mark. I'm one of the co-founders and the head of machine learning at a company called ProteinQure. We're a computational biotech startup that originally got founded as part of the first quantum stream at CDL back in 2017. So what we do is we focus on the computational design of peptide therapeutics, which we specifically use to do targeted drug delivery. Our biggest breakthrough lately has been starting a phase 1 clinical trial with the first AI-designed peptide. And we'll probably talk about that as part of this panel, but over the years we pivoted away from quantum computing and nowadays mainly focus on simulating molecules and supercomputers and using generative AI.
Hi everyone, I'm Sam Mugel, the CTO and one of the founders of Multiverse Computing, also a CDL alumni from 2019. Actually, when I first went through the program, Mark interviewed me, and thanks for letting me in. You're welcome. And so, Multiverse Computing, we do a lot of things, but nowadays, so we started out in quantum science, focused on finance, and slowly pivoted, and now what we do is a lot of AI compression, a lot of specialized LLMs for industry. And I also came back as a CDL mentor, so I've been doing that for the past 3 years or something.
Yeah, it's amazing. I didn't know the story about the interview part of this, and so you were impressed, right?
Of course, yeah. We've actually been friends ever since.
All right. Oh, okay. Very good. Very good. Okay, so let's. I'm going to start this off with. We'll start actually with you, Mark. What has been the biggest surprise for you about the role that quantum has played with your company or your experiences, and particularly over the last 10 years? We'll start there.
Sure. I still remember back in 2017, there was a lot of excitement. It was kind of the early years where the first quantum chips came online and were able to be used by the public through the IBM Quantum Experience. And a lot of people kind of expected things to go exponential, similar to like a Moore's law type trajectory. And I think I'm probably not alone that I'm quite surprised that we hadn't quite seen that kind of progress on the hardware side. Which has a variety of reasons. There's a lot of engineering challenges, and Christian could probably speak more to that. But what surprises me even more so is on the theory side. There really is it's not restricted by the hardware. You only really need a pen and paper or maybe a marker and a whiteboard to derive a new quantum algorithm. And I would have expected to see way more quantum algorithms being developed over the last, let's say, 8 years. And instead what we've seen is kind of a dequantization of certain algorithms. There's a very famous algorithm called the HHL algorithm that was underpinning a lot of quantum machine learning. And there was an 18-year-old undergraduate student at the University of Austin who basically disproved that quantum speedup and showed that it is indeed no faster than a classical algorithm. And so, yeah, that's, I guess, what I'm kind of surprised by, that we haven't really seen many more polynomial or exponential speedups in the theoretical quantum algorithm space.
Okay, Michael, I saw a lot of head nodding to that. Comments from you or any other big surprises you want to add? And then Sam.
Yeah, so first, really surprised by the number of multi-billion-dollar market cap public quantum companies we have, which is fantastic to see, because I think, as we heard from Christian, it's a great way to continue to raise capital, and these companies need a lot more capital to get to where they need to be. I would echo that it's also a little bit surprising the hardware hasn't advanced further, given some of the big names behind it and the large amounts of money raised. For us, there's a little bit of a personal story where our work in quantum actually helped us secure a key customer for our main materials business. And we were raising our Series B 4 years ago. We were working with their business unit and working with a research team that was evaluating some of our quantum algorithms. And the research team said, this is the best thing we've ever seen, better than anything we can buy commercially, better than anything we've developed internally. And the business unit said we had nothing of value, that our products were useless and they didn't want it. And then there was an internal fight where someone high up was like, wait a minute, I'm getting one team that tells me they have the best software and algorithms for simulating materials, and the team that actually want to sell their materials to saying it's useless. And like, something must be wrong here. And they got them together and said, no, you have to evaluate these materials. And that customer now, we are going to mass production. It's going to be in 50 million consumer devices at the end of this year. All right. Thanks to quantum, it's like part of that story getting there.
All right.
So that was a big surprise.
Yeah, no, that is surprising. Sam, any comments on that?
I wanted to echo what Mark said, actually. I was really surprised that there was so much excitement back in 2015, or when we started the company in 2019, around quantum algorithms. And I find it incredibly surprising that there's so few new ones that have come about. Like, almost all algorithms can be basically mapped back to two algorithms. Maybe to add a little bit onto that, I think I'm really surprised by how fast variational algorithms have kind of been abandoned. There was, like, for a 10-year period, it felt like everything, all theoretical research was either like in error correction or in hybrid algorithms. And now we're at a stage where, at a very exciting stage where at scale error correction is in sight, basically. And suddenly, like, everyone's turning around and saying, okay, well, hybrids are no longer relevant. Like, now let's only focus on that scale. And it's kind of, well, why did we spend 10 years working on this? You know?
So then I guess what's in your quick take, what's the solution here? Is it just a misunderstanding? Is it a reframing? Is it how can we think about what the future looks like, Sam?
Well, maybe it's just like what Christian said, like just let's put these machines on the market, let's get people to play with them. We also know that we also know classes of problems where these machines are relevant. I'm not entirely sure.
I mean, I think it's, again, back to what we heard earlier today. Predicting the future is really hard. And I think it's hard for, we talk about exponential speed up, like the concept of exponential mathematics is just not easy to understand as humans, because it's not something we normally experience in everyday life. And so when you think about when this hardware is fully realized, what's it actually going to impact? Probably the biggest impact nobody knows today, because we don't have those capabilities. And yes, it could be a shock disruption, yes, it could break encryption, but then encryption will change and we'll fix that. And so then the bigger impact after that is going to be something nobody's probably thought of today until the machines are actually built. And that's why we have to continue to invest in the hardware and continue to invest in the software and continue to play around with different applications.
Yeah, okay, that's well said. Mark, do you have anything to add on this point?
I don't really know a good solution for that, but I guess one thing that I often notice is that in quantum algorithms research, at least 10 years ago, it was mainly physicists working on things.
Yeah.
And I think over the years what has changed is as more people from machine learning and traditional computer science have kind of brushed up on their quantum skills, and they might come in with completely new mindsets, different ideas, different approaches that maybe a theoretical physicist wouldn't necessarily come up with. So maybe that's just kind of where we need to let things develop a little bit more and kind of get fresh inspiration from different fields.
And I think that happens naturally as you're going to make the algorithms more abstract, basically, and as there's access to software that just solves a problem, basically. And I guess the hope would be that when we have access to all these disparate tools, that you're able to combine them in some really smart way that's going to accelerate stuff, right?
Do you think we need more domain experts that learn quantum computing rather than people on the quantum side trying to apply it to different domains?
I wonder about that, because I find that domain experts often get caught up on like, oh, here's this thing that's blocking us. And sometimes it's a bit more about like, okay, tell me what you're actually trying to solve, rather than like a quantum computer, like algorithms for doing Monte Carlo aren't that good, but maybe if you look at the entire pipeline, maybe there's a better way to do it.
Yeah, and so maybe the solution is, I mean, I go back to, Michael, what you said earlier, is like just put it in the hands of folks in different stages and we won't even know. And so some of those are domain, some of those are going to be domain specific, some of them will be playing more generally, and then we'll just basically see what happens. There might be a triggering event which actually changed the discourse.
Yeah, exactly. And I think our group of theoreticians, some of the best theory they developed was because they were playing with the real quantum hardware. Right. But it was the limitations of the hardware. They found a limitation, they got really annoyed by it, and were like, let me figure out a way to get around that, and came up with a new idea, and it turned out that idea was actually more valuable than the original problem they were trying to solve.
Okay, so you said very clearly that, and we've heard this all day, it's hard to predict the future. So let's predict the future, because I think it's fun. And I love a good hot take, and so now, and I also see a bunch of quantum folks in the room, so what's something that each of you thinks will happen in the next 5 years with quantum that 75% of your quantum colleagues wouldn't agree with? Right, 20 seconds each, because why not?
I'll rephrase a little bit. I think that the end winners are companies that haven't been founded yet.
All right, I like that.
And so that gives a great opportunity to the next generation of entrepreneurs to build the companies that will be scalable in this space.
And so we're taking applications right now for CDL Quantum, so just keep that in mind. It's the next great company. Mark?
My hot take centers around the statement of quantum chemistry having its ChatGPT moment right now. It might be the case in material science, it's not my domain, But in drug discovery, I think that is not the case. Having worked in the field, I used to be of that opinion, and I'm still very optimistic when it comes to quantum. But over the last 9 years, I kind of realized how simulating a molecule more accurately or predicting the binding affinity to 2 digits after the decimal isn't really what drug discovery and pharma is bottlenecked by. It's really by the messy biology, the experiments. Like our first trial is about triple-negative breast cancer, and we're right now working on a type of brain cancer. And there it's all about getting molecules, designing molecules to cross the blood-brain barrier. And these kinds of problems are not really addressed by any quantum speed-up or better quantum algorithm.
Okay.
But there's a lot of classical algorithms and AI that we can use to tackle these challenges.
Great. Sam, close us out here.
My hot take is on the business side. I think that even once we'll have all the technology available to build an at-scale quantum computer, actually like bringing all of that together at scale is going to be such a huge financial investment that's a massive barrier that we're going to have to cross to get there.
All right. I think a lot of people would agree with that, but but fund it is the thing that I will take away from that too. All right. Thank you guys for this really exciting panel, really exciting contributions, and man, I look forward to the next 5, 10, 50 years of quantum. All right. Thank you again.